Good morning. Thank you for coming. My name's Alistair Forbes. I work at CCP Games, London, as lead core tech engineer. Thank you for waking up early to come to this talk. I'm going to be speaking about wall hacks and why we care about them at CCP London in our game, and how we solve them on the server side. Click. Okay, so I'm going to talk about what a wall hack is exactly, why they happen, why we were motivated to prevent them in our game. Then I'm going to cover our approach to solving the problem before moving into a deeper dive into the implementation. Finally, I'm going to wrap up with some remarks on how well it went and some performance data before taking any questions you might have. So what is a wall hack exactly? We at CCP London are working on EVE Vanguard, an MMO FPS where action takes place in a series of alien worlds. Our level designers work hard creating environments for players to explore and fight in, thinking about cover and sight lines, hiding places, loot crates, generally to create tactically interesting encounters. Wall hacks essentially undo all that work, exploiting information on the client that the player shouldn't know about, effectively giving cheaters the power to see through walls. Here's an example of a simulated wall hack in our game. It's taken from a locally running instance, and I've put in the player viewport data that the client knows about where enemies are. So put enemy locations and distance and little green targets on their back. And as you can see, it kind of reveals where enemies are, giving players like an unfair advantage. Okay, so to talk about how we fix the problem, I'm going to go into a little bit on why it happens. To cover some basics, the architecture of a multiplayer game like ours is that there exists a central server which contains the game state. It knows everything about the game and coordinates the action amongst multiple game clients. The process by which clients kept up to date about what's happening in the game is called replication. For example, to simplify a little bit, when a client joins the game, an actor representing that player is replicated across all the clients in the game. And as they move around the world, their position and other attributes are continually replicated as well. And this goes for the enemies, loot crates, and other game objects in the world, and is essentially what drives the immersive multiplayer experience. When an actor should exist on the client and receive updates, we call it relevant for that client. Common relevancy metrics used by Unreal's replication system are to use distance from the player. For example, each actor has like a net cull distance outside of which that actor will stop being replicated for that client. And there are other systems such as grid spatialization, which apply that concept to optimize for open worlds, many actors. What these systems don't take into account is what a player can see, or what they should be able to see and hear. So they expose that information unnecessary to the client. So to fix this, we fix it on the server side by only replicating what the player should be able to see, what they should be able to hear. The system was originally conceived as simply visibility-based replication. And we called it fog of war because it was catchy and because it described more generally the approach of using environmental factors to limit what the client should know about. Taking visibility first, the question becomes, of all the game objects in the world, which ones does the player have line of sight on? So we use server-side line tracers to establish line of sight by continually tracing between the player and other actors and finding out where traces get blocked. We can determine whether that actor should be replicated for the player. The image here is a screenshot showing some fog of war debug visuals around an NPC. Hopefully you can make out the little green dots in the image. They show the location of where line traces are being made around the NPC to equivalent points around the player. We make traces on the visibility channel, and they run asynchronously to not block the game thread. And we use simple test traces because we don't care about what blocks the trace, only whether it is. If any line traces are blocked, if any line traces are not blocked, then line of sight is established and the NPC is considered unfogged relative to the player, and vice versa if it's a player. For example, since all the line traces here are not blocked, the NPC is being replicated. And here's a short video showing this in action. So there are some NPCs hiding in this geometry, and are marked with bright red line to show when they're being replicated. And as we glimpse them across the half pipe through the window, we can see that the actors are appearing on the client. But when they move out of view, they stop being replicated. So it kind of keeps their position hidden unless we can see them. So what do we have to consider when designing the system? The two main concerns are fidelity and performance. So there are a couple of ways that the system can fail. It can replicate actors that the player shouldn't know about, which rewards cheaters, or it can fail by not replicating actors that the player should be able to see, or replicating them late, which is kind of gameplay destroying, which hurts gameplay for everybody. Pop-in joke. Actors are not points. They have volume. An actor standing partially obscured by scenery might happen to have a trace point blocked and incorrectly fog that actor. But it would be impractical to trace across a whole area of an actor. So we have to choose points carefully to kind of ensure coverage while not being ridiculous in the number of traces we're making. The footage I've shown has shown a pattern where we establish through testing where we have a couple of widely spaced points and points clustered in the middle, which in practice tends to work for the kinds of levels that we have. Replication lag is another important concern because when you begin replicating an actor to a client, it doesn't appear immediately. There can be a lag of up to a second. Which again great pop-in. On the flip side of fidelity is server performance. Like if you think about a fully loaded server with 18 players and 200 game objects, that's like thousands of pairs. And if you multiply that by say 8 or 9 traces per pair, that would quickly overwhelm the server. And we aim to hit 60 frames per second on the server. So that's we need to try and think about how to avoid that. And we also need to replicate audio. So we want to be able to hear players we can't necessarily see. And we want to make sure that teammates are still unfogged relative to one another. So the first thing to notice, we obviously don't need to perform a line of sight check every frame. We can exploit that closer actors probably require more fidelity because pop-in would be more obvious, and more distant actors, they occupy a smaller radius on the screen, so we would require fewer visibility points to establish line of sight. We can also be more relaxed about checking actors that are already unfogged. It doesn't really hurt gameplay that much if an actor is visible for a few extra seconds when it goes into cover. And it's probably preferable to not fog and unfog repeatedly if an actor moves in and out to cover, to avoid replication costs of re-replicating repeatedly. So we can exploit these little these opportunities for optimization, and we can establish a trace budget per frame. So we ran in our game a commandlet that randomly traced across the map repeatedly to kind of figure out a reasonable number of traces we could make every frame that wouldn't overrun the server. And so these are sort of level of detail parameters that we established. So for very close actors, we want to be able to very accurately tell if we can see a player. So we use 9 tracers, and we check every single frame, since popping was probably most obvious at that point. But for more distant actors, we can be much more relaxed. Like, at least on our levels, line of sight, the kind of lines of sight we have mean that we can get away with checking like every half a second, and using comparatively fewer traces. And for really distant actors, which are essentially points on the screen, we can be even more relaxed again. And when unfogged, we can also just check quite infrequently too. So we solve replication lag by projecting visibility points ahead of where the player is moving. So if an actor has a movement component, then we look at the velocity component of their movement and move the trace points correspondingly. This shows that in action. This NPC is running back and forth, and we can see that the points are being projected ahead of them, which essentially gives us time when they run out from behind the wall. We've already seen them at the point that they appear, so they're fully replicated. Without that projection, they would just sort of pop into existence, sort of like past the end of the wall. So to handle audio, we use the idea of exposure events. So we can, the fog of war system is aware when an audio event plays. We log an event of a certain radius over a certain time. And within that radius, that player or NPC will be unfogged for players around them. I can hopefully demonstrate this here. So this tirelessly running NPC is running back and forth, and we can hear within this boundary, this yellow boundary, their audio is being replicated, and we use that radius as well as line of sight to determine whether to replicate them. So when they fall outside that boundary, they stop being replicated. It's worth bringing up the need to perform extra checks, because to bring up example of this guy standing in this little half pipe, you can see that some of the visibility points that we're using are actually outside of the walls that they're standing in. They overlap, which means for players standing next to them, next to the wall, this NPC would always be unfogged. So we added a second check to verify that any point that establishes a line of sight can be traced back to the parent actor. So every line of sight check actually requires 2 traces to confirm that they should be unfogged or fogged, which is very helpful for reducing accidental unfogging. And here's an example of the system running in EVE Vanguard. You can see there are enemies behind this ridge. This is the wall hack simulation that we had earlier, so we can kind of see where everyone is.
Don't come any closer.
When we enable fog of war, it hides everything that we're not supposed to see.
Don't come
This guy we can still see because he's on top of the ridge. And then we can see the people down again there when we reach the top, as you'd expect. So how do we do this? I'm going to run through a high-level overview of what we implemented to make this happen. The work consists of 2 main components: a subsystem, fog of war subsystem, which is a game engine subsystem running whenever the game is, and a custom replication node, because we use RepGraph. So we implemented a node that uses the fog of war status to decide what to replicate. The subsystem tracks fog of war actors, it performs visibility checks, handles audio exposure events, and emits events as appropriate. A fog of war event is just a map of player actors the lists of actors that have been fogged or unfogged. So it's only sending information when things change. Looking a bit deeper into the subsystem, it maintains an array of unique visibility pairs, which are pairs of actors that can be fogged relative to one another. And the subsystem hooks into actor creation destroy delegates, and it looks for specific classes of actors to decide what to include in the fog of war pairs. A unique visibility pair consists of a player and any other object which is foggable in the game. And the main thing that this subsystem does is iterate through those visibility pairs. I put some pseudocode for the tick function that's executed every frame. Essentially, it checks to see whether, because traces are asynchronous, we look for the results of the previous frame's checks first. And if anything's changed, then we emit the fog of war event. And then we add any scheduled visibility checks to a list and sort that by lateness, and then run through all of the checks up to our trace budget, forming line of sight checks. I've added, at the bottom, you can see there's a sort of escape hatch condition, where if we exceed the trace budget for a frame, we make all close pairs visible, which is like reduces load on the system because they're the most burdensome to check, and minimize hopefully any pop-in caused by pairs not getting to be checked in time and sort of falling behind and popping in a bit late, replicating late. The visibility pair is the handles, well, it contains a state of all the state required for checking two objects, the time last checked, when the next check should occur. It has functions for performing the checks themselves, taking into account level of distance, and also handles audio exposure events. Audio exposure events we implement with a component that can be attached to any actor, and it has a function for adding an event which declares that owner unfogged for the appropriate time. Exposure events unfog just one member of the pair, unlike line of sight, which unfogs both. And the custom replication node that we implemented, it's based on Epic's dynamic spatial frequency repgraph node, which dynamically modifies replication frequency of actors depending on how far they're away from the player. We implemented that node and moved the dynamic spatial frequency calculations to a background task, which saves a fair bit of time on the game thread. And it also looks for fog of war events and uses them in deciding whether or not to replicate an actor. We also have a custom replication graph which instantiates this node, and we found we had to filter RPC events on the fog status of an actor to prevent issues where sending an RPC event to an actor that is fogged would briefly create that actor on the client and then uninstantiate them after the call had been processed. So we implemented the system in our game midway through development. So we already had some levels of gameplay written, and we sort of added the system, and we discovered that the main issue was that actors would be written on the client, not sort of expecting actors to persist on the client. They weren't really written for actors, considering actors would disappear for like due to fogging. For example, projectile owners would disappear being fogged while the projectile was in mid-combat. So essentially, the work was to add a lot of safeguards around that. We also had issues around the visibility channel occasionally, like not being configured properly, so actors would fog in full view of the player. So it's like a long process of adapting what we had to work with the system. Turrets were particularly troublesome because they were embedded into scenery often, and this would hide visibility points within the scenery and cause them to fog erratically. And performance-wise, it runs quite well. You can see on this trace graph, this real insights graph, there's the bottom there is the background task containing all the raycasts for the system, and at the top left, the tick for the foggable system, where it's checking results and performing fogging and unfogging. Runs like it tends to run under half a millisecond on the game thread, and perhaps up to a millisecond on the in the background task, which is acceptable for our purposes. We have it running with all players, NPCs, and loot boxes in the game, and in testing, it's generally proven to be good enough for our purposes. Yeah, so that pretty much is my talk. Thank you for listening, and I'm happy to take any questions you might have.